So recall we ended with the following result, which was proved by Athanasiadis. So we have that G is the incomparability graph of a natural unit interval order. So that makes G a natural unit interval graph. Let lambda be a partition of n, then the coefficient C lambda P is what we'll call it, of Z lambda inverse P lambda in the power sum expansion of omega x G x T is the sum over all tableau in NP lambda in G, the row word of T. And we'll call that NP lambda of T, that polynomial. So recall that NP lambda is the set of all fillings of a Young diagram of shape lambda, in which the rows have no P descents and no left to right P maxima. And RW is the row word. Okay, so Athanasiadis' proof is what I'll describe next. So the ingredients. One, an observation. So three things that came from our paper. The first was an observation expressing or relating NP lambda T to NP T, where there's no lambda, so that just means we're looking at all permutations that have no P descents and no left to right P maxima. So that's just, or one row tableau, either permutation. So lambda then would be the partition with a single part n. The second ingredient was our special case. So John and I proved the special case where there's just one row or just one part in the partition. The third ingredient was our decomposition in the basis of fundamental. Quasisymmetric functions. So this came from the paper that we're discussing now, paper with John. The fourth ingredient was a lemma implicit in the work of Reutemann. And this transfers decomposition in the fundamentals to decomposition in the power sum. So that's what this lemma does. So I'll talk about the ingredients. So first was this observation relating NP lambda to that. So let's look at an example. P, let's say, is this post set. Which we've seen many times before. Okay. And lambda, we'll let that be 3, 2, 1. So that's a partition of 6. So T is, here's what we'll let T be. And we can check to see that each row has no P descents and there's no left to right P maximum. So this is N and P lambda. And let G, well, usually it's the incomparability graph. So but let it be, it doesn't matter what graph it is. Let G be any graph on N, on 6. So we don't have to be distracted by what graph it is. And if we look at the number of G inversions of the row word of T, so what we need to do is just take the G inversions of each row, whatever G is. And then we have to include the inversions that go across the rows because we're looking at the row word. So the G inversions, we'll call it the row 2 of a set composition. So that'll be 2, 3, 4, 5, 6, 1. So this is a set composition. So like a set partition, only the order of the blocks matters. And so the inversions that we count would be, there's an inversion here to 1. There's an inversion. The incomparability graph would be the path, but it doesn't really matter right now. Just the inversions that occur between these blocks. If 3, 2, 3, 1 were inversion, here we would count it. Okay. So in general, so we'll say that given a tableau, let B of T be the set composition formed by rows of T. And inv G of the row word of T then is equal to the inv G of B of T plus the sum inv G of the row I of T, where I goes from 1 to K. K is the number of blocks. So from this it follows, so I hope that's clear. From this it follows that this sum is equal to the sum over all set compositions T to the number of inversions, G inversions of the set composition times P alpha belongs to NPI T to the number of G inversions of alpha, where NPI, where PI is equal to the poset P restricted to the block BI. So that's how we can relate these just the permutations with no P descents to, we can relate this polynomial to this one.
So Michelle, on this product or the sum on the far right, should that be n sub p sub I?
On the far, this here? Yeah, that should be n. So p sub I, where pi is the restriction. That doesn't look like an I, is that?
Looks like an L to me, but.
Oh, thank you.
Never mind.
Okay. Okay, so that's what the piece of. Okay, so these are this brings us to the special case that John and I were able to prove, because the lambda here has only one part. So that's the second ingredient, was the special case. So that says that that sum on the far right is the coefficient of 1 over lambda I, P lambda I, partition with a single part, in X, in comparability graph of PI, XT, and let me call the coefficient C lambda I, PI. Okay, so that's the coefficient. That's our special case. And the reason this works is because induced subposets of any natural unit interval order is a natural unit interval order. So that's why that works. And now we can plug this into this. Into this. And we have NP lambda T is equal to the sum B in set composition lambda T to the inversion, number of G inversions, B C lambda I PI What did I do? Yeah, okay, so we have now this is, so we have this. Okay, from here, replacing this by that, we get this. So we want to show, in order to complete the proof, we just need to show that C lambda P, because we're trying to show this equals this. So C lambda P is equal to so that's how the coefficients are related. That's what we want to show. And then we'll prove the theorem. We can show the coefficients are related this way. That's Athanasiadis. That was his approach. So the third ingredient of his proof was the decomposition that appears in my paper with John. Into fundamentals. And here's the theorem. And this, the t equals 1 case is due to Chow. Shortly after these, the chromatic symmetric functions were introduced, Chow proved the following result in the t equals 1 case. Let P be a poset on N, and G is the incomparability graph of P. Then omega xg is equal to the sum over all permutations in Sn, T to the inv G of sigma F des, so P of sigma. So that's the P descent set, the place where there are P descents. And so we just added this to his result, and our proof is very much is the same as his. We didn't have to do anything clever to make his proof work. And I'll talk about the proof of this next time. And I'll talk about some applications. Well, I'm going to be talking right now about Athanasiadis's application of this, but I'll talk about other applications next time. So the fourth ingredient in the proof is the lemma of Yuval. So here it is. Let g of x be a symmetric function over the over a commutative algebra. Q algebra. And let g of x equal, when we decompose it in the fundamentals, where alpha s belongs to R, because it's going to be a polynomial in T in our purposes. Okay, then the coefficient of Z lambda inverse P lambda in the power expansion of G of X. It should be a period. Is S belongs to U lambda minus 1 to the S minus S lambda alpha S. So let me say what this is. Is that readable? The cardinality of the set S minus this other set S lambda minus 1 to that times alpha S, where S lambda is the usual set representation of the composition lambda. So lambda, I said, is, well, here it's clearly a partition, but we're viewing it as a composition, writing it in decreasing order. So S lambda is the set associated with that composition. So that's lambda 1 plus lambda 2, the partial sums, lambda 1 plus lambda 2 plus lambda k minus 1. K is the length of lambda. And U lambda is the set of lambda unimodal subsets. Of n minus 1. Okay, so I need to say what a lambda unimodal subset is, but for the other than that, I think the result is clear. These are certain subsets. You sum over those subsets using the coefficient of the fundamental alpha S. I'm leaving off the alpha, the coefficient. I left off the n here, but so I guess there should be an n there, but n is fixed. So that's how you get the coefficient in the power sum expansion. So to say what the unimodal sets are, I'll just do an example. So let's say lambda is 4, 3, 3, and that is, we're viewing it in a way as a composition of 10. S lambda is then 4, 7, the partial sums. And then how do we get a lambda unimodal set? We list all the elements from 1 to 10. Okay, actually we can leave 10 out because it's a subset of n minus 1. So it should only go up to 9 because n is 10 here. N is 10. Okay, so I'm going to put the elements of S lambda, there they are, 4, 7. And then to get a lambda unimodal set, I choose any initial segment of in here, and in here, any initial segment of those sets. So let's say I choose 1 and 2. There's an initial. I can't choose 1 and 3. I can choose 1 and 2. So I need an initial segment. So I chose 1 and 2. I could have chosen the empty set. I could have chosen 1, 2, 3. I could have chosen 1, but not 1 and 3. And then I do the same here. This time I'll choose 5 and 6, an initial segment. Okay, and now I'll choose the empty set. Empty set counts as an initial segment. So I've chosen initial segments from those partitioned, from that partitioned set, from each of those blocks. And then I'm free to choose any of the elements of 4, 7, of that set, of S lambda. So I could choose 4, 7, the empty set. I could choose, I'm going to choose 7. Okay, so those are the choices I made. Any subset of S lambda is okay. But only initial segments of the other sets. And so we end up with the set 1, 2, 5, 6, 7, and that's the set. Where 7 was that part, that element that belonged to S lambda. So this is an element, this is a lambda unimodal set where lambda is 4, 3, 3. So Athanasiadis applied this to our decomposition. Oops. So that means that alpha S in his theorem, the coefficient of the fundamental, is just this. T to V. Okay, so that's the coefficient of the fundamental F sub S. Okay, this is a sigma. So now the coefficient, according to Weichmann's lemma, is of, remember we were denoting the coefficients of the power sum corresponding to lambda, then becomes and here's the alpha sub S. Oh, yeah. Okay, so this is the alpha sub S in Weichmann's lemma. And we can rearrange things. We can sum over all permutations in Sn, -1 to the descent set, the permutation, minus S lambda, key to the number of inversions, the permutation. And then, it's not quite right because we can only sum over the permutations whose descent set is in U lambda. So that means the descent set has to be lambda unimodal, the P descent set. And that strange terminology, lambda unimodal, will be explained when we think about descent sets. Okay, so what does it mean? For the descent set, the permutation to be lambda unimodal. Well, it just means that you have if we write down that set of numbers 1 through n, the descent, each segment will have an initial segment, there'll be a descent, a P descent. And then after that, it's not really going up. It's just that we're saying that there's no P descent. Till we get to the element of S lambda, P descent again. It's not really going up unless that descent, unless P word was just a linear set, a linear order. So it's just not. So these segments all are, we could say the segments are P segments of sigma. Are P unimodal. In a different sense that I was talking about unimodality the other way, now we're going down and up rather than up and down. So we're going down, the permutation goes down according to the post set P, and then does not continue to go down. It doesn't really go up, as I just said. So let's look at an example that hopefully will make this clearer. Lambda is 4, 3, 3, the same example we had before, which is a partition of 10. S lambda is 4, 7. Sigma is 8. I'll write sigma in 2-line notation. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 8, 5, 3, 10, 6, 4, 2, 1, 7, 9. So that's sigma in 2-line notation. And let me take the elements of S lambda here, 4 and 7. Okay. And if you remember what lambda unimodal set is, it's a set initial segment, an initial segment here. So that corresponds to these descents. And let's just assume that every descent is a P descent to make it. So let's forget about what P is. We'll just assume every descent is a P descent. In this example, just for this example. So here are the descents. Okay, so those are the descents of the permutation. And you can see that in each segment, the descents are an initial segment of the of that segment. So if I write this permutation as a tableau, so the first segment, including the element of S, the element corresponding to S lambda, so 8, 5, 3, 10, then 6, 4, 2, and then 1, 7, 9. So I wrote it as a descent, as a tableau. So we fill each row. Well, okay, so I hope that's clear how I did that. T is now this. And the shape is lambda. And now let's look at the P descents in each row. Okay, there are the P descents. We're assuming every descent's a P descent, so those are the P descents. And so we can see that if we count P descents in each row, we get the number of descents of the permutation, but we don't count the elements of S lambda, because the elements of S lambda, those are descents at the end of a row. So we're not going to count this or this, this or this. Okay, so we're really counting P descents in each row is the same as counting the descent, the P descents of the permutation minus that S lambda, throwing out the less than. So now let M lambda P be the set fillings or tableaus of Young diagram of shape lambda with distinct entries in N and with P unimodal rows. Okay, so each row, the entries go down and then they don't go down. Down, this goes down all the way. This just goes up. I shouldn't say up, it doesn't go down according to P. So according to Reuteman's lemma, C lambda P is equal to I'm just repeating what I had before. That's okay. And that we can replace by these T's in MP lambda. And then this becomes that. And this can now be written as B is a set composition of type lambda, T in G, the set composition, I equal 1 to K, minus 1 to the des P I T of sigma oh, I forgot some T to the inv sigma. Wait, I'm sorry, I'm skipping something. Sum over sigma in SPI minus 1 to the and sigma is pi unimodal minus 1 to the des p sigma t to the inv. Okay, so that turns into that, which is t to the inv by Yuval, by Reuschmann's lemma applied to pi. We have and shape lambda I. And that's exactly what we set out to prove, that this decomposes in this way. And so that's what we needed to prove, I said earlier, and that's what we've accomplished. So this is by Reuschmann's lemma. Okay. Oh, I said SPI here. Yeah, so we're permuting the elements of PI. Over here, we're permuting the elements of PI. I hope that's clear. Some consequences of this result. The characters of Tomachko's representation of the type A semi-simple Hessenberg variety are positive. So that's one consequence that comes from this, the combinatorics. The people working in the geometric side of things did not have this result. So this follows from the Brosnan-Chow proof of my conjecture with John. And the second, another consequence is that this also gives a decomposition of LLT polynomials. In the P basis. P lowercase p, there are two kinds of P's here, power sum, in the power sum basis. And this is work of Carlson and Nelleth and Jim and Andrew Wilson, that you can decompose the LLT polynomials in the P basis. So this follows from the P decomposition we've been talking about. There are some other combinatorial descriptions. Of the coefficients. I forgot if I did the, I put the P on top and the lambda. One is due to Scandara and Hyatt, and I think there are other authors. And the other is due to my former student, Brittany Elsie. And she gives another combinatorial description, which she obtained by considering a generalization to directed graphs. I'll talk more about that next time, about her generalization, her decomposition in the P basis. Okay, but now I just want to talk about, I don't know if I hope I'll finish. I want to talk about the theorem, our decomposition in the fundamental basis that we just used in the proof of the decomposition in the P basis. So this is the result I just talked about, that Chow did the T equals 1 case. So now G is the incomparability graph of any poset, and that implies that omega GXT, of course, these posets, P is a poset on vertex set N, or any ordered set.
Michelle, did you mean to write omega XG?
Oh, no, I did not.
Oh.
Thank you. Oh, yes, you're right. But yeah, I did not mean
okay.
Okay. You're right. So that's equal to T to the NG that's equal to that. So let me sketch the proof. So let A OG be the set of acyclic orientations of G. So that means we're just giving each edge a direction, and so that there's no cycle, directed cycles. For each A, for each acyclic orientation of G, let CA, oh, I used C too many times. I realized I use it for coefficient. Now I'm using it for coloring. B, oh, this is a capital C. The set of acyclic orientations of G. No, what am I saying? A is an acyclic orientation, B the set of proper colorings. I'm rushing too much. Proper colorings. C of G that are compatible with the orientation. So by compatible, I mean that CI is less than CJ if there's an edge from I to J. So the coloring goes up if there's an edge. This gives XG of XT. We can sum over all acyclic orientations T to the ascent set of A, C. So we were calling that the ascent set of the coloring, but the ascent set of the coloring only depends on the acyclic orientation associated with that coloring. So that's CA XC. So we can group together the coloring, the proper colorings that are compatible with a given acyclic orientation. The ascent set of the coloring is the same as the ascent set of the acyclic orientation. So the ascent set, that's just where we're going, where there's, if the edge is oriented this way, then the color here, then let me say this, if the edge is oriented this way, then the ascent goes from I, and we count that as an ascent. If I is less than J, that's what I forgot. If I is less than J and it's oriented this way, that's what we call an ascent of the orientation. So each acyclic orientation each A, I'll just say each A determines a poset PA. And that's, let me do an example. So let's say we have the graph, this graph, and we'll give it an orientation. So this is our original graph. We give it an orientation like this. And there are no cycles here. Okay, and so this is the acyclic orientation, and the poset that corresponds to that will be, we'll direct the edges downward. So here's 1, down to 2, 3, down to 2, and 2, down to 4, or down to, yeah, there's an edge from 2 to 4, so we'll go 2 down to 4. Oops. And there's an edge from 3 down to 4, but since this is a Hasse diagram, we don't include it. So this is P. So now we're going to consider strict P partitions, this poset. This is the same as proper colorings, compatible with the acyclic orientation, what I just described a minute ago. So those are the strict PA partitions. And so K, notation from my first lecture, this generating function for the strict PA partitions is C, the colorings, proper colorings compatible with the acyclic orientation, X, C. Okay. So by Stanley's theory, of P partitions, I talked about P partition reciprocity in the first lecture, but now we're going to use a different result. You can write this generating function for strict P partitions, let's say P is any subposet, as the sum over all linear extensions of the poset F descent set of the product of U, I'll say, and sigma This is the product in Sn where U is any fixed decreasing labeling of P. Just fix any labeling and it'll work. This gives you this generating function. So xg, we apply this to xg, xt using this. AO, acyclic orientations of G, T to the S. So, and now we can write, we can replace this by this. F des U, that U was the decreasing labeling, and now it's of a particular post set determined by the acyclic orientation, multiplied by the linear extension sigma. So we're fixing a decreasing labeling for each of these post sets P sub A bar, and that's equal to, we can rearrange sum over all permutations, T to the A, the acyclic orientation determined by the permutation. And here we have F des U. Now that's the acyclic orientation determined by the permutation. Because there's one permutation, there's a unique decreasing, well, how should I say this? So the permutation determines an acyclic orientation, and that's what A bar of sigma is. It determines one for which this has to be true. So there's a unique, and that's what we're calling U A sub bar sigma. For which this is true. There's a unique acyclic orientation for which this is true, so that's what we're using here. And then we note two things. When we note one thing, this is easy to see, that this is the same as in, you just need to think about it for a minute, that this is true, so we can replace this by this. And then it's harder to find a decreasing labeling omega. Not omega, I better use something different than omega. U of P A of sigma such that, I'm sorry, I changed notation here. This should be A sub sigma. And this should be A sub sigma. Such that, and this takes some work, find a decreasing labeling U of P A sub sigma such that des U sigma is equal to the complement of des P sigma. So that allows us to make so that makes this become, become in this, and this become this. And so, and this, hence, omega xg xt, because omega takes complements and in the fundamental basis. And I ran over, I'm sorry, but that's where I wanted to, what I wanted to prove. So that's the decomposition using P partition theory. We'll see some other applications of this result next time and generalizations.
Okay.
Thank
Well,
you.
thank you, Michelle. Thank her again. Good.
Thanks.
Any questions for Michelle? So I had a question actually about the last, what you talked about at the end of the last lecture.
Okay.
So
Should
you
I?
were looking at these n p lambdas, and you said it's still an open problem to prove they're unimodal.
Right.
Right. But you know that they're palindromic.
Right.
Right. Yeah.
Palindromicity. Yeah, that's pretty straightforward to prove.
I just wanted to comment. So one of the things I did in my thesis was to prove Garcia and Remmel's Q hit numbers. Ferrer's boards are palindromic and unimodal. And so they depend on Ferrer's board, which we can think of as a Hessenberg vector, and also a positive integer k, which is between 0 and n, where n is the length of the vector. And I was able to do it by showing these Q hit numbers are sums of Q hit numbers for smaller boards times Q binomial coefficients.
Right.
And when you multiply those out, that preserves this palindromicity and unimodality.
Right.
And they all end up to be centered in the exact same spot. When you add up these things, then I was just wondering if that might be something like that going on here.
Well, so there is, so you can do that also for the Eulerian polynomials by writing it as sums and products of unimodal. That's kind of what you would describe it.
Yeah, so there's special cases of these Q hit numbers, so it's probably the same thing.
Oh, right. So okay, yes. So that's when I say that, so then you can do that also for the path, which you're describing, to show E unimodality of the path. You can do something like what you're describing. But for P unimodality, let me go back to this. So this is what we can decompose it this way. The problem here is that I think this is pretty much a decomposition like this.
Right.
Maybe what you're saying would work, except that the center of symmetry. So these actually, we can show that these are unimodal polynomials, palindromic and unimodal. So we do have a product of palindromic unimodal polynomials, as you would describe it. The problem, so this product would be palindromic and unimodal. But then when you multiply by the center of symmetry changes. So you're adding palindromic unimodal polynomials with not necessarily, maybe it could be, something could be done with this along the lines you're suggesting, but these are not These do not have the same center of symmetry, so when you add up, you don't have palindromic unimodal.
I see. So you'd need a different decomposition.
Maybe, yeah, or maybe a clear understanding, but it doesn't seem to be have the same center of symmetry. If you rearrange these B's, then the inversion changes, but this doesn't change. These terms don't change. And
So
this would change,
yeah.
so you'd get a different center of symmetry, so that's the problem.
I see. So if you wanted to use this one, you'd have to hope that if you sum up these T to the M's over some B's that fix the others, that happens to be. Luckily, okay.
Yeah,
I think that answers my question.
Okay.
So any other questions?
I just want to make a comment. We have another formula, right, for the coefficient of the P lambdas, which might be more amenable because it's a product of T numbers, right, which has the desired property times a smaller sum, right? So you could attempt to apply this kind of thinking to the smaller sum, right, and maybe prove something, but I have no idea how to do it.
Yeah, that's yeah, we should take a look at that. Right. And there are other descriptions, so maybe one of the other ones would give the unimodality. Yeah, I forgot to mention, we have another description too of the coefficients in our paper. That's right. Thanks, John.
Okay, anything else? No. Okay. We'll see you on Thursday then.
Okay, and thank you, everyone.
Well,
Bye.
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 Thank you.